Hey, hi guys. Hey, hi there. And so in today's video, we'll be covering the last part of hypothesis testing, which is ANOVA. Okay, ANOVA one way. So let's first import the libraries from scipy import stats as stats, import numpy as np. Right. Once we've imported everything, now let's say we have a data set which is called as plant growth. Okay, there's an Excel sheet which I have the data, and when I read the data, right, you will see that it consists of different types of plants and their respective growth. You can see here the type of the group, which is the type of plant and the weight, not height, but the weight of those plants. Okay, great. So now if you look at this column, we don't require this column because it has nothing to do with it. So I'll simply remove it out. I'll select only the weight and the group. So this is my data frame. Okay. So for one-way ANOVA, we should use the inbuilt function, which is stats.f underscore one-way. And inside that, we can put all the necessary array of data which we have, the sample data points, and it can easily give you the hypothesis. Okay. Null hypothesis will say there is not much significant difference in the tree groups. Alternate hypothesis will say there are significant differences with respect to each group. So since we need the x1, x2, now what is x1, x2, x3 here? x1, x2, x3 will be three individual group of data points. And here, this will be record to the group which we see here. So if you look at the group, df underscore ANOVA of group, right, dot unique, if I do, you can see these are the three groups: CTRL, control, TRT1, TRT2. So with respect to CTRL, TRT1, TRT2, I need the weight data points separately because these will form the three samples of my data, right? So weight. So what I'll do, df. So how will I extract it? Very simple, simple level slicing, right? Which I've already done before, right? What is the main condition? The group should be equal to, let's say, CTRL. If I do this, I'll get everything. So what I'll do, I'll again use it to slice it from here. Okay. And next I'll extract the weight part out of it. Once I extract the weight part, this is again a series. I need the exact values. This is the array, right? So typically this weight selection, you should do it afterwards. Okay, guys, so that it does not throw any warning. Okay. All right. So once I have this, I can simply save it in x1, x2, x3, whatever variable you want to use. Alpha, I'll be using alpha at 0.05% as we had already used before, right? Confidence, I don't require. Okay. And then I'll use the function which is stats.f underscore one way. And this function requires the three sample data points. Very simple, x1, x2, x3. And I'll definitely get the p two-sided. This is again two-sided. So two-sided p value I'll get, right? And I'll compare with alpha. So if you remember, if you notice here, p value is 0.015, which is less than alpha. So we'll reject the null hypothesis, right? Which means that my that these three samples belong to different population, right? They belong to different population. Or you can say there's a significant difference in weight among the three groups. Okay, so these three samples definitely belong to the two different population. Okay. Now, if I want to do two-way tests, there are two-way tests also available with with when we have dependent groups that you can easily figure it out. We can simply Google it and search it, right? Two-way test ANOVA Python, right? Okay. And there you have all the functions available as well. Okay. I'll just share the link with you guys. Okay. All right. So let us take another example from the slide. Three groups of samples of factory emissions of different plants of the same company were collected. The score is computed based on the composition of the emissions. We want to find out if there is any inconsistency or difference across the three groups. So these are the groups of emissions with respective emissions. right, from their respective plants of the same company, right? This is something which I already done in the slide. So what I'll do, I'll record all these individual data points in a separate lists. Okay, I'll specify what is the null hypothesis and the alternate hypothesis separately. I'll denote the alpha. So alternate hypothesis will be there's a significant difference of emissions across the three different plants, right? And null hypothesis will be there is no significant difference. All the means are same. So I'll use again f underscore one way. We already have the three samples segregated out. We put it here. I'll get the f test and the f statistics. I'll run this first, right? So once I already have the three sample points segregated out. I'll put it here in the function, and from there I'll give f statistic and p value. So you can see the p value is less than the alpha, right? And of course, it means that the null hypothesis will be rejected. There is a significant difference in the two groups of plants. If I now want to calculate, suppose the f critical, what do I need? So f critical, just like we have stats dot chai2.ppf. Similarly, we have f.ppf, right? f.ppf, stats.f.ppf. What does it require? It requires three things here. 1 minus alpha is, of course, it's required, right? Then you need the degree of freedom, right? In certain cases. So here we need 2 degrees of freedoms. Why? Because we have the degree of freedom between and the degree of freedom within. So in certain cases, it will be written as numerator and denominator. Remember, we did ms mean sum of squares with respect to between, and mean sum of squares with respect to within give us the f statistic value, right? So that's why this is in the between mean numerator, within means denominator. So sometimes in certain books or documentations in Python, it will be written as numerator and denominator. Degree of freedom, numerator, degree of freedom, denominator. Numerator means B between, denominator means V, W within. Numerator means B between. So DFB, DFW. Now, how was DFB and DW calculated? DFB was between K minus 1, where K denotes the number of groups which we have, right? And within was n minus k, if you remember, guys. Total number of samples minus the number of groups. Correct? These are already mentioned in the slide. See, n is nothing but the length of all the elements. K is equal to 3 because we have 3 different elements, 3 different groups, sorry. And DFB is k minus 1, DFW is n minus k, DFT, total degree of freedom, is n minus 1. We actually do not need this in our calculations. So let me run this first. Okay. And then now since I have DFB and DW, I can easily calculate using the F critical. Stats.pf.ppf 1 minus alpha, stats.f.ppf 1 minus alpha, comma 2 degrees of freedom in this case, DFB and DFW. So let's see what is the F critical value. So the F critical value is 3.16 and here it is 5.6. So F statistics greater than F critical. So null hypothesis will be rejected. Same way. So whether you calculate from that side or this side, it's the same, right? Okay. Let's, can we now try to calculate the F critical for the previous case? Okay, let's see. So what do we need in this case? So I'll remove this part also at the below. Okay, so I don't get confused. This is for two-way. And I have to make this as markdown. Okay. Okay. So first thing which we need to do is, what is K? K is a number of groups is 3, definitely. N is nothing but the total number of data points, right? Total number of data points will be how much? Length of x1, x2, and x3, right? Same way. Length of x1, right? So we got N and K. Now I need degree of freedom between, which will be K minus 1, and degree of freedom within, which will be N minus K. Got it? Next, what I'll do, I'll simply try to calculate the F critical value. So F underscore critical will be stats.f.ppf. 1 minus alpha, comma, df underscore between df underscore video. And I can also calculate. This is 3.35. This is 4. So null hypothesis will be rejected. Clear? And I can also copy paste this directly. Okay. And this is accept and reject. Okay. So we don't need, we have not specified these statements. So I can just simply ignore this. Right? Okay. Can do cell run all also, just to be sure. So this is how you do it. So, or we can compare f underscore stat with f underscore grade. That's it. All right, guys. So this is how you do ANOVA test in Python. Very simple, guys. Okay. I'm sure ANOVA is one of the most widely used statistical tests. People often use Excel sheets also to do ANOVA test. There are other ways of doing ANOVA test, the two-way tests, right? With replication, without replication, all these can also be done. I've specified the link here so that you can go through it. Okay. Right. This will also help you understanding the F ratio, which we typically get from linear regression stats models in Python. We'll go to that later on in machine learning modeling. So this is how you basically try to understand ANOVA using Python, how we implement ANOVA using Python. It was very simple, right? You can simply just use one line of code to extract the F statistic and P value as well. Whereas in the slide, we saw there's a huge calculations which goes behind, right? We need to calculate sum of squares between, sum of squares within is calculated, total minus sum of squares between. And then again, if you remember, right? Sum of squares between, sum of squares within is calculated, sum of squares total minus sum of squares between. Then we would also calculate, this is fine. We have to anyway calculate here also. But again, you have to calculate MSB and MSW, right? This divided by DFB, this divided by DFW. Finally, we get this, and then we take the ratio, and then we get the F stat value. Then we compare with the F table, and then we get to know the conclusion. But here, just one line of code. As simple as that. Okay. That is all for today in this video. And we'll come up with more examples. We'll come up with case studies also with respect to hypothesis testing. So do stay tuned, and hope you are learning, guys. Hope you're enjoying. Most importantly, please keep practicing. See you in the next video.